So any questions? So just the two components. You want to find the internal versus external. And internal no change. External will change by the factor S. All right. So this is the delay, and then we are going to finishing up the lecture 14, which is the energy and power for the inverter. So this is the reference chapter, and the sequence video. So here we are interested in the power and energy consumption of the inverter. And there are two components in the energy and power. One is called active dynamic switching energy and power. So you see that this inverter is charging and discharging the capacitance, the CL. So we will have this power consumption by the charging and discharging. So this is the first component. And when we say this active dynamic and switching energy, that means the input is switching. So you have the low to high, high to low. So your input is switching like this. So you are charging and discharging your capacitance. So you are consuming the power and energy. But the second power, this static power, means input, no change. So input stay at 0 or 1. So if your input stay at 0 or 1, we are consuming so-called static power. So this is due to the subthreshold leakage current we discussed earlier. So we will talk about those two contributions in the next. But first of all, you need to understand there are two contributions. One is called the active dynamic power when the input is switching. The other one is static, means input, no change. Okay, so let's look at the active power or the dynamic power. So for example, if the input is changing from 1 to 0, your output is changing from 0 to 1. So in this process, we say that PMOS is working. PMOS is pulling up the output, because initially output is 0, finally output is 1. So it's pulling up, and PMOS is for pulling up. So in this process, the NMOS is like open circuit. So this goes back to our RC equivalence. So in this RC circuit, what kind of energy do you consume? So you are charging this capacitance here. Initially the voltage is 0, and eventually the voltage is VDD. So we can look at the power consumption from two aspects. First one is from the power supply. So here you have power supply VDD. So from the power supply, you are providing the constant voltage VDD. But the charge is coming from the power supply to charge this capacitor. So how many charge do you get eventually? Eventually, the voltage on the cap will be VDD. So the charge on the cap eventually is C times VDD. And this charge comes from the power supply. So you know the energy is this is Q. Energy is Q times VDD. So then the energy will be C VDD squared. That is the energy coming from the power supply, VDD. But on the other side, if you look at the capacitor, this load capacitor, CL, during this process, because this voltage is changing from 0 to VDD, on average, you have half VDD, the voltage. And if you look at the capacitor itself, the Q is changing from 0 to Q VDD. But the voltage is changing. On average, you only have half VDD. So the energy stored on this capacitor is half of this CVDD square. So that means eventually you will store half CVDD square energy on this capacitor, CL. But from the power supply, you spend CVDD square. So my question is, how do you explain the difference here? So from the power supply, you consume CVDD square. But for the capacitor, you only store half of that. Any idea? So here you lose half of the energy to where? It says here, E, dissipated. So you are dissipating the energy, half of the energy from the power supply to this resistor. So your current is flowing through the resistor, so it's consuming the power. And the energy dissipated in this process is half CVDD square. So it's that you provide CVDD square in total, and half of that stored on this capacitor, and half of that is dissipated. So my question here, this energy becomes what? Dissipated means what? Any idea?
Heat.
Heat, that's right. So you are consuming the current through the resistor. So you are heating up the resistor. And the energy dissipated as thermal energy is this C half CV square. So this is the output low to high transition. So you see that we have this energy consumption here. And after, let's say, this is a half cycle, half clock cycle. You have the input high to low and output low to high. And next half cycle of the clock, input from low to high, then output from high to low. So in the second half, then you can say that you are going to discharge the capacitor from VDD to ground. Through the NMOS, and PMOS is open circuit in this case. Because this is a high to low transition. So in this process, it's simple. So eventually, you get zero voltage on the capacitor. That means zero energy stored on the capacitor. So that means initially you store half CVDD square, and eventually you store zero. So that means all of this half CVDD square is dissipated in this discharge process. So you see that here you consume half CVDD square through the NMOS, again as a heat. So to summarize this, in one clock cycle, you are consuming, let's say, first cycle here. Here this is NMOS consuming half CVDD square, and then the next cycle, PMOS here consuming half VDD square, half CVDD square. So in one cycle, the total energy you consume is CVDD square. This is due to charging and discharging from the capacitor here. And all the energy eventually comes from the power supply, but divided into two half cycles. So if you consider the clock frequency, this F is clock frequency, then you will get dynamic active power. So essentially, you know the power is energy times frequency. So it's say VDD squared times the clock frequency F. If you're running faster, of course, then the power will be larger. So that's how we get this equation for the dynamic active power for the inverter. So any questions here? All right, so let's go to the static power. So this is different. So this means the input does not change. Okay. So if input, let's say, stay at 1, your input stay at 1 or stay at VDD. So you know the NMOS is on, PMOS is off. However, if you look at the PMOS transistor, it's off, but it's actually in the subthreshold. Subthreshold condition. Why is that? Because the VGS, this is G, this is S, this is D. So this VGS is VDD for PMOS, and the VDS, so this here and here, so the output is 0, right, VO. So it's also VDD. Oh, sorry, made a mistake. So here, the input stays at VDD, so this VGS is 0. So VGS is 0, and VDS is VDD. So this is exactly the definition of I/O. If you go back to the lecture, I think lecture 11, or maybe in lecture 10. So this is the definition of I/O. That is the subthreshold current, if you see that. So that is this current. This current is when you have this condition. So you still have this I/O current. And then this I/O current is coming from the power supply. So the power, you know, is current times voltage. So that's why you have VDD times I/O as the static power. So that explains why even your cell phone is in the sleep mode, you are still consuming the power. The power you're consuming here is the static power instead of dynamic power. This dynamic active power here is you are doing the computation. That means you are switching from 1 to 0, 0 to 1. So you are charging and discharging, then you have this power given by this equation here. But if you are in sleep mode, you are doing nothing, but your input is kept at 1 or kept at 0. Still you have the current I/O going through the transistor. So that will give you the static power. So a few more words on the short circuit current. So this is for dynamic power. This is for dynamic. I should move this slide earlier. So the dynamic power actually is due to the current flowing through those two transistors. Mostly it happens during this transition in the VTC curve. So during this transition, then you will get the largest current. In this case, both NMOS and PMOS current will be somewhere here. Or if you look at the current versus the input voltage, so let's say if you have the VTC curve like this, you switch the input from 0 to VDD. Then your current will be largest in the transition. And if it's matched, then it will be largest in the half VDD. So that is the peak current through the inverter. If you think about the inverter current as a function of the input voltage, this current as a function of the input voltage, that has this kind of relationship, ID versus input voltage, will be the largest when the Vi reaches the Vm, and in this matched case, it's half VDD. So you have this kind of so-called short circuit current. Because at this moment, that both transistors are on, and they pass the same current from the VDD to ground. So during this short period, it's like you have a short circuit current from the power supply to ground. So that's why it's called short circuit current. Okay, so to summarize, so we have two power consumption in the inverter. The first one is active dynamic power consumption. So this is due to charge and discharge that load capacitor. And in one clock cycle, it's C VDD squared. And the average power is F. F is clock frequency times this C VDD squared. And typically, we will add this alpha as a switching activity factor in front of this. This alpha means how many percentage of the clock cycle you are going to switch. So not every clock cycle you are going to switch in the practical circuit. So this is a percentage of switching of all the cycles. So maybe in the practical circuit, maybe 10% of the time you are switching your input. 90% of the time you stay there, unchanged. So this alpha is just a switching factor, activity factor. The second power consumption is the static power, which is I off times VDD. So in total, you have those two components. That's why the total power consumption is this dynamic and static. And delay is if you use that CVDD and half I average. So this I average is mostly affected by on current. So delay is proportional to 1 over on current. So that means if you want to make your circuit faster, you want to increase the on current. So the way you increase on current, as a circuit designer, you can increase the W over L, and then you get on current larger, delay smaller. So that's the end of the lecture. Any questions?